So, good afternoon. Sorry for small delay, but we can finally start. The topic of today's lecture is, we have actually several topics. We will start with the first topic, which you can see here, which is called Bentley rules. And then we will continue talking about compiler internals and how to profile your code so that you can get as fast code as you can. Bentley rules. What is Bentley rules? Bentley rules is a book. Or actually, it's not a book, but the rules were written in a book. The book was written by Jan Bentley in 1980 something, and it was called Writing Efficient Programs. And in that book, the author wrote several ways how programs can be optimized and how programs can be written so that they are fast. Nowadays, some of those rules are no longer applicable, and you will see why, because nowadays those rules are already implemented inside the compiler, and we will see which ones and how to benefit from it. But still, there are still many things which are useful to know about and which you can apply. If we are in the next slide, we will go through the rules one by one, and I will talk a bit about each of the rule. And if you think about that, you will find, oh, it's clear. This is like trivial. Yeah, of course it's trivial. It's just a simple optimization. And if you think about the problem a bit, you will figure that optimization yourself. So it's no rocket science, nothing complicated. But I think it's useful to see the list of the rules one by one, because typically, if you optimize your program, there is not just a single optimization that can optimize the program. Typically, you have to apply several optimizations together, and only if you apply all of them, the result is like good. So it's useful to know what are the common optimizations. If you are thinking about optimizing your code, you can just look at the list and try to apply the optimization one by one and so on. So, what are the Bentley rules? On this slide, we don't mention all the original Bentley rules. Here we have something which is called new Bentley rules. This is slightly updated and filtered set of those rules which still applies today. And yeah, we will go through of them. In general, all those rules can be classified into 4 classes. In order to optimize a program, you can change the data structure, somehow optimize or change data structures so that you can get a faster program. You can optimize loops because a typical program spends more or less like 90% of its execution inside loops. So if you are able to optimize loops, you can optimize a lot of time where the time is spent. You can optimize some logic expressions, do some simplification, shortcuts, or whatever. And finally, you can optimize functions, how functions are called, and basically reduce the overhead of function calling. So we will look at these one by one, and we start with data structures. So the first optimization that you can apply to data structures can be called packing and optimization. So for example, imagine you have a lot of data, and by data I mean like information, and one part of the data is a date, like day, month, and year. So naturally, if you if you store this, you will use, I don't know, like integer for year, another integer for month, and another integer for the day. And this will need, I don't know, depending on the size of your computer, this will need like 12 bytes or something like that. Or you can think a bit about whether you really need integers for all of this. And clearly, for months, you just need 12 different values. So you don't need like full integer, full 32 bits for storing the months. For storing the months, you just need 4 bits. Similarly, for the day, you don't need 32 bits for the day. You can have 31 days in a month, so you need 5 bits. So what you can do, how you can optimize this data structure, if you are in C, you can remember that if you are defining a data structure in C, you can use this syntax that after the type and field name, you can type a double colon and the number of bits. And this is a way to tell the compiler, don't use the full integer, use just a 13 bits integer size, and the compiler somehow magically reorganizes the structure so that it stores year in 13 bits, month in 4 bits, and so on. So by doing that, the whole data structure uses just 22 bits. And if you remember from last time, where I told you that the memory is perhaps the slowest part of your computer, making the size smaller can be useful from this point of view, because whenever you are reading the data from memory, memory is slow, so the less data you read, the faster you can read it. So this is one way how you can make your program more efficient. On the other hand, calculating with this bit size data can require some overhead, so you often need to do so-called unpacking and decoding, like convert the data from one representation to another, where you can compute with the data faster. And whether it's beneficial to do this separate unpacking and decoding or not, directly calculate with this data structure, it really depends on what are you doing. If you are doing a lot of computations, maybe it is worth first unpacking and then calculating on top of unpacked data structure. If you are doing just a simple calculation, but you need to traverse a lot of those structures, it might be beneficial to just read it and calculate directly in this encoded packed structure. So that was the first optimization. Another typical optimization which you can apply in your code is called augmentation. And this stems from the fact that the data structure you use for your data can also influence how fast you can access the data. So here you can see a trivial example. You have data in a single linked list, and if your algorithm requires, for example, adding data not only at the beginning, but also adding data to the end of the list, so you need to add some data to the beginning and add some data to the end, having single linked list would be inefficient, because if you need to add something to the end, you would first have to traverse the whole list from the beginning to the end, and only then you can add the list. So what you can do, you can augment your data structure, like increase your memory consumption, but this increased memory consumption will lead to faster execution time in some operations. So for example, in this trivial example, you can add one pointer, which will always point to the last element in the list. And now whenever you want to add something to the end, you just follow the single pointer without traversing the whole list, and the addition is typically faster. Similar tricks can be done with different data structures. In many cases, you just trade execution speed for memory. Sometimes it's beneficial to use as little memory as here to get faster speed. Sometimes you can use more memory to speed up some operations like list additions here. Another optimization which is used quite often, and this will be also one optimization which you might be able to use in today's homework from the lab classes, is pre-computation. In many cases you need to calculate something, and this something can be calculated pretty expensively. So what you can do, if you somehow know beforehand, ahead of time, what needs to be calculated or what will need to be calculated later, you can pre-compute it at compile time or at the beginning of runtime, depends on how you decide to do it, and then use just the pre-computed values. To give you an example, imagine we want to calculate so-called binomial coefficients, which is the value from combinatorics. This formula, you probably remember it from some statistics. And the input is two numbers and a k, and you calculate this formula by performing some computation. The computation, you calculate the factorial, and you can calculate the factorial in many ways. Specifically, to calculate this formula, you can end up with this recursive function. So in order to calculate this formula for 1n and 1k, you calculate the same formula for n-1 and k-1, and you add it with the same formula for n-1 and k. So graphically, this can be represented like this. You are calculating. This is the value of n. This is the value for k. And if you are calculating this value for this n and k, you can do it by summing the value one row up and one row up and left. So by calculating it this way, using a recursive function, would be pretty inefficient, because for every calculation you need to do a lot of function calls, a lot of recursive function calls, and so on. So what you can do instead, you can create a table or an array where you basically pre-compute those values. And if you, for example, know that in your program you will use n and k, which is smaller than let's say 100, you can use a fixed size pre-compute table for these values. At the beginning of your program, you just pre-calculate those values, and instead of calling the function recursively, you just look at the row above, which has already been calculated in the past. So you can calculate this function just when you start the program. This is possible. The disadvantage is that you will have to wait after starting your program for this pre-computation to happen. So if startup time of your program is also important, don't do this. You have several other options. One of the options is to initialize this pre-computation table at compile time. So one simple way of doing that is just writing all the values manually to your source code and using so-called brace initializer in C or C++ and initialize the array this way. The result of this will be that this table will be part of your binary, of your executable file, and whenever you run your executable file, this data is already loaded automatically to the memory and can be directly used. Of course, manually creating this table is not very nice. If you want to change the formula somehow, you would have to recompute this table by hand. So what's often used these days is so-called meta-programming. Instead of writing a program to calculate that value, you write a program to calculate that value during compilation time. So one simple thing is to write normal, for example, C program, which will just generate the source code. And during compilation of your program, you will compile this program, execute this program. As you can see, this program uses printf, and it just prints this table to its standard output. So it generates this source code, and then you can compile this source code during the compilation. So this is how things were being done, like, I don't know, 20, 30 years ago, that you wrote special case programs to generate the code. Nowadays, modern programming languages have those meta-programming facilities built in. So, for example, in C++, you can use so-called template meta-programming, and you can use it to perform the same without actually compiling another program and running it during your build process. The compiler will automatically pre-compute the table during compilation. Similarly, Rust has very nice feature. Rust has very nice macros. These are not like C and C++ based macros where they can just replace pieces of text. In Rust macros can operate on syntactic data structures of the compiler, and so it's a very powerful tool for all these kinds of meta-programming. So pre-computing is a nice thing. If you pre-compute some often used calculation, it can speed up the program pretty much. But sometimes you simply don't know which values will be used in your program. You know what is the maximum value. For example, here this 10, you perhaps don't know it. So similar techniques, but not so static, is called caching. If you know that there is some value which can be computed, but this computation is expensive, and you know that it's quite likely that you will use the same value later, you can just remember the already computed value for next time, and if the same value is needed later, you will just use these remembered values. So, for example, here is a function which allows you to calculate hypertenuse of a triangle. You specify the length of two sides of the right angle triangle, and you calculate the hypotenuse value. This is pretty simple calculation, but you see there is a square root operation. If you don't remember anything from this course, remember that square root is one of the slowest basic mathematical operations that computers can perform. So whenever you need to use square root in your mathematical computation, think about how you can avoid this square root, and you will get significant speed ups by not calculating square root. So here what we can do, the simplest cache is just that we will remember a single value. We will have global variables like a, b, and the result. And then if the function is called, we first check whether the arguments to the functions are the same as the last used values. If yes, then we just return the previously stored result. If not, we remember the values and calculate the result in full. Of course, this is the the trivial implementation of cache. You may want to store maybe not a single value, maybe you can store 10 last values or 100 last values or so, depending on your computation, and apply something more efficient. Another thing which can be exploited to get faster programs in mathematical computations is sparsity. Many algorithms require some matrix operation, matrix vector multiplication, matrix by matrix multiplication, and whatever. And in many real-world problems, many of those matrices contain zeros. And if you remember how you can multiply a matrix by a vector, if you implement this algorithm for matrix of size n, here it's 6 by 6 matrix, the number of operations, the number of multiplications and addition will be n squared, 36. But given that only 14 elements are non-zero, you know that multiplication by 0 is 0, and addition of 0 to the result doesn't change the result. So basically, it's wasteful to calculate with zeros. So instead of calculate with zeros, half of the calculations is completely useless. You can decide to change how is the matrix stored. Instead of storing it in a 6 by 6 array in memory, you can use more efficient data representation. So this not only saves you the memory, but depending on how many zeros you actually have, but it can also save the computation time. So this is a way how you can store the same matrix, and you use just 3 vectors, rows, columns, and values. In the values, you just store all non-zero elements like 3, 1, 4, 1, 5, 9, and this rows and columns vector encode like which index into this array is valid for which value. So the advantage of this is that if you are doing many calculations, you just go through this memory sequentially, one by one, and can easily access the values. And yeah, and if you want to calculate how much space you save, instead of using n squared memory to store this, the storage needed for this value is just n plus nnz, which is the number of non-zero numbers. So the storage can be reused. Now, how you can multiply this matrix by vector. So instead of doing this textbook algorithm for matrix vector multiplication, you do it a bit more sophisticated way. This is the data structure, this is the algorithm, and basically what you end up with is that you have exactly this amount of scalar multiplications. Instead of 36, here you will have just 14 scalar multiplications to get the result. So the algorithm is more complex, but execution time will be much shorter, and it will be even shorter if you have more zeros in the matrix. So this is another useful technique. And the last or another example of this sparsity exploitation technique is how to store a graph data structure. If you have a graph like this with nodes and edges, there are many ways how this can be stored. One way is like every node is a data structure. These edges are pointers. Every node has a dynamically linked list or whatever of pointers to the other nodes, and so on. Or you can use also similar structure as we have used for the matrix, where you have just a single array of edges, and this array tells you what is the destination of the node. So if you go here, this is vertex ID 0, and you will see those two numbers are the node numbers where the edge is going from 0. So it's 1 and 3. Here the edge from number 2 is 2. Sorry, the edge from number 2 is here 5, and there is no arrow, so it goes nothing, and so on and so on. So this way you save both memory and computation for certain algorithms. Different algorithms may benefit from different data structure. So the point is that the data structures and your algorithms should match. Now we can move to the other class of Bentley rules, and these are logic-based rules. Here, many of those or some of those rules are already implemented by compilers. So, for example, constant folding and propagation. This is typically implemented by compilers nowadays. What's the point? If you have a program like this, and you want to calculate the volume of, this is the radius of Earth, and so on. So you can calculate the volume with this formula, and you can see that many of those calculations, for example, radius squared, is already used somewhere else. So if your compiler is sufficiently good, most of today's compilers are sufficiently good, they just calculate this value just once and then reuse the result here where the same value is needed. And in the end, because everything is constant here, the compiler will not have to calculate anything at runtime. Everything will be pre-compiled at compile time because of this constant propagation. Similarly, common sub-expression elimination. This is, I have already covered that in the example before. If you have a common sub-expression like here a minus d, the same value b and d can be calculated, or actually d don't have to be calculated again because the same value would be here, this b. The same is not true for a and c because it's b plus c, but b is changing between calculation of a and c. So good compiler will calculate b and use the same result for d, but will calculate a and c differently, because the results should be different. Another useful way to speed up your program, and this also might be something which you might benefit from today's homework, is to use algebraic identities. So here the goal is to check, you have two like balls and given by their center coordinate and radius, and the goal here is to check whether two balls overlap or collide with each other. So how you can do that? You can calculate the distance between the centers of the balls, and if this distance is greater than sum of the radiuses of those balls, then they do not collide. If not, then they collide or just touch. So naive way of calculating that would be just to perform this calculation And you remember what I said before, square root is very slow operation, so maybe it would be good idea to avoid this square root to make things faster. What's the goal? Here we want to calculate whether this d is smaller than sum of two radiuses. And the algebraic identity which you can use here is that if square root of some number is greater than square root of another number, then it's the same as the number is greater than another number, provided that they are both positive. So instead of calculating this and checking whether this condition is true, you can actually calculate just square of all those conditions, which means that instead of calculating one square root, you will have to calculate just one square, but multiplication is much faster than calculation of square root, and therefore the result will be faster. So this is the formula. You just calculate the diameter, the distance squared, and you compare it with the square of sum of two radiuses, and it will be faster. Another thing, short-circuiting. Imagine you have a function which checks whether the sum of elements in an array exceeds certain limit. So a naive way how to implement it is just to go through all elements in the array, calculate the sum, and if the sum is greater than the limit, you just return whether it's greater or not. On the other hand, you don't always have to go through the whole array to know the answer. For example, here you can check whether the sum is greater than the limit even inside the loop body, and whenever the result is true, you can immediately return and you can skip traversing the rest of the array. Depending on the data in your arrays, this can be beneficial or not, because even this comparison costs you something. So if you know you have long arrays with high or big numbers and low limits, this can be beneficial. If you have short arrays with very small numbers, this is probably useless. Ordering test. This is a typical thing. There is an implementation of a function is white space. Many times whenever you process text, you go through some characters and you check whether the character is white space, like it's a carriage return, tabulator, space, or new line. If you do it like this, it would definitely work, but you can take advantage of knowing that the frequency of certain characters in the text is different than the frequency of another. So if it is like human written text, probably there will be more spaces than tabulators, new lines, or carriage return. So by first checking whether the character is space, it's more likely that you will hit the true condition just after the first comparison, and you would be able to skip those other comparisons, and this will speed up your execution. So you can use it if you know some statistical properties about data. Sometimes you don't know it, or sometimes you think you know it, but you didn't verify it, and you are wrong. People are often wrong in these like judges, that thing. One way to make this automatically is profile guided optimization, which is a topic that we will talk about in the second part of the lecture. Fast pass. Fast pass is another common optimization. We have the same problem. we have to calculate whether two balls collide with each other or not. And there is one way how we can calculate it really quickly. Instead of calculating some square roots and squares and whatever, we can bound each ball with a bounding rectangle or bounding box. And if those bounding boxes do not overlap, we know that the balls do not overlap as well. So this is so-called fast pass, because comparing whether bounding boxes overlap is just a matter of very simple comparison. You just subtract two values and compare it with the size of the radius. There is no multiplication, there is just addition and subtraction, and this is a fast operation. So this is called fast pass, and only in this fast pass test fail, then you may go to the precise computation, where you calculate full square of the values and do this slow pass, which is precise. So basically, you can use this technique if you have some imprecise but sufficient test for the condition. You first execute fast sufficient test, and only if this sufficient test fails, you go to full-fledged computation, which takes long time. Another computation, and now I can do quickly. This is typically something what compilers can do pretty well. So you have lot of conditions, lot of ifs here, and this is one way how you could implement addition of single bit numbers in software. This is probably not what would you do, but this is just an example. And as you can see, there is a lot of ifs, if those numbers are 0 and so on. So what you can do, you can just create a table of those input values and create a combinatorial table of those values and the results, and just implement this table in your code. So instead of having a lot of ifs which are somehow nested and so on, remember from last week, you know that every if there is a potential for branch prediction miss, which can slow down your execution. So what you can do, you can somehow calculate the row in this table, and depending on that row, you can just quickly return the result based on the row number in the table. This can be sometimes faster, sometimes not, depending on how this calculation is expensive. Another class of optimizations are loops. Many of those are really well implemented by the compiler, so I will just go through it very quickly. So loop hoisting. The goal here is inside the loop, everything which is inside the loop body is calculated, executed many times in a row. If there is in this loop body, if there is some piece of code which is invariant with respect to the loop variable, here it's I, you can just move this calculation outside of the loop, compute it just once, and then reuse it in every loop iteration. So basically, you can calculate this expression in front of the loop and then just use it here. Today compilers are pretty good at that, and in many cases the compilers can figure this out on their own, so you don't have to think about it much. But if your expressions here are more complex, the compilers can fail figuring this out, so you can do it as well. Sentinels. This is quite useful technique. Compilers can't do these things usually. Only in some simple cases, but this is quite clever technique. If you have a tight loop, like this. This is again, we are checking whether there is some integer overflow by summing all the elements in the loop. The code can look like this. You just calculate the sum, and then you do some comparison in the loop body, and then return. The thing is that in every iteration of this loop, you are checking for two conditions. The first condition is this condition whether there is an overflow or not. And the second condition is this loop ending condition whether I is smaller than n. Since the operation inside the loop is pretty simple, it's just an addition. So there is just one addition and two comparison. If you are able to remove this single comparison, you can, for example, save 1/3 of execution time of this loop, which is quite significant. So how can you do that? You can do it by modifying the data so that this condition will be triggered not only when it is in the data, but also at the end of the iteration. So instead of checking whether you reached the end, you just add an artificial element of data, at the last position of the array, you add, in this case, this will be the highest possible integer number, and having this highest integer number there ensures that that there will be integer overflow, and this is what this condition, these conditions check for. So then you convert this loop from for loop to while loop. There is just one condition, and you know that this condition will be true either in the middle of the array or at least at the end where is this artificial edit element. Then after you exit the loop, you just check which of those conditions was true and return the true or false depending on the result. So yeah, this is how you can speed up fast inner loops. Another technique, loop unrolling. Loop unrolling is in every iterations you have to check this end condition, and there is also instruction like jump to the back. So by unrolling the loop, you can reduce all of these overheads. So for example, if you have loop and you know this loop is always executed 10 times, instead of having to execute this loop like this way, you can write the loop this way. There will be no overhead in this iteration variable. There will be no overhead in checking for the condition. This will be just faster. Compilers can do these optimizations for you. If you have fixed number of iterations and this fixed number is quite small, this is what compilers typically do on their own if they think it's a good idea. So this is so-called full loop unrolling. Another useful technique, compilers do it as well, but sometimes you can help, is so-called partial loop unrolling. So if you need to sum some numbers in your array, but you don't know how long the array is, what you can do, you can, for example, in a single loop iteration, you can sum like 4 numbers. The advantage is that you save the overhead of the loop iteration by 4 times, because there will be not a single jump every iteration and single comparison, but there will be jump and comparison only every like 4 iterations. So this is nice. The disadvantage is that if the length of the array is not the multiple of 4, you will produce wrong results. So at the end, you have to just finish the sum for the remaining elements if it is not multiple of 4. So you start from where you finished before, and you continue until the end. Even this, the compiler can do automatically. Another benefit of this is that if you perform operations like this, you can use vector instructions like SIMD instructions to perform multiple additions by a single instruction, and this is what compilers can do also well. And another technique related to loops is loop fusion. Again, the goal is to reduce the overhead caused by code looping. So instead of paying this overhead twice, because you are iterating from 0 to n, you can just put those two loops together. There is just single overhead of one iteration, and in both code you just execute. The bodies of the original loops. And last but not least, another optimization is elimination of wasted iterations. So for example, here we are comparing whether some values, or we are swapping the values in an array. And we are doing that by doing only the triangle of the array, not full array, but only one triangle. So if you iterate on both sides from 0 to n, we are basically wasting half of the iteration, because this condition will be false in half of the cases. So in half of the cases, we will just go to the next value of j and I and do nothing. So instead of doing that, adding condition to the loop body, you can modify the indices so that basically this condition would be always true. You iterate from 1 to n, and then you iterate from y instead of 0 to from 0 to y instead of to n, and basically you implement the same condition as is implemented here. So these were techniques how to optimize loops. And last but not least, last technique is about inlining, code inlining or function inlining. You probably know that inlining is a technique which is again used and implemented inside compilers. If you have very simple function like square here, instead of calling that function, you can just copy the body of the function directly here, and you will save the overhead of calling the function. So compilers can do these things automatically. If they see that the function is sufficiently simple, they can do this inlining for you, so you don't have to think about it much. Or you can even help the compiler. You can tell the compiler by specifying the function as inline. Typically it's used in combination with the word static. And this is not typically it doesn't mean that the function must be inline, but this is typically a hint for the compiler saying, yeah, this is a good idea to inline that. And if the compiler thinks it's a really good idea, depending on some heuristics it has implemented, it can just inline it automatically. So the keyword is inline in C and C++, and other languages have it as well. Yeah, and then recursive functions. Again, compilers are pretty good at that. Implementing functions in a recursive way is not really good idea, because every call to the function needs to allocate memory on the stack, and in many cases it's not necessary to allocate the stack. So if you have so-called tail recursion, that the last thing which function does is call itself with another parameters, this tail recursion can be replaced with a while loop, so that you don't call itself allocating memory on stack, but you just iterate in the loop. Again, compilers can do this automatically, so you don't have to think about that. Another way what you can do is recursion coarsening. So instead of doing like one invocation per iteration, or by doing like recursive invocation for small numbers of here n. This is like sorting algorithm. You can if n is sufficiently small, you can, instead of going to the recursive function, you can use some more efficient sorting algorithm. Here it is simple insertion sort, and this way you can also speed up your sorting algorithm by switching between recursive and non-recursive implementation. Yeah, so these are Bentley rules in a nutshell. So to conclude this part, good idea in optimizing your code is to first get your code correct, and only after your code is correct, you find where you can optimize it by profiling. We will talk about profiling soon, or by applying some of those rules, because you already know where it could apply, and apply it only after the algorithm is done. You should not do all this optimization blindly, because just blindly applying all those rules make no sense, because sometimes there is always trade-off, depending on what is in your data, how big your data is, what values are there. So some optimizations works only in some cases, some others in different cases, and whether the optimization is actually effective, it's not clear, especially nowadays when the hardware is quite complex. Hardware does a lot of optimizations, and ensuring that simplifying and reducing the work of your program actually translates to lowering execution time is not clear. Compiler does much of this work for you, but not everything. So you should know what is done by the compiler, and this will be the point of the next lecture, or next part of the lecture. So let's see. Let me see what I have here. I don't have it here, so let's do it differently. Yeah, so now let's talk about compiler and profiling. I will change the order in this lecture a bit. I will first talk about the compiler, because this directly follows to what we have talked about in these Bentley rules, and then I will talk about profiling, which will be what we will need for exercise today. So going directly to the to the compiler stuff. So you already know from last week that we have at least in the Linux world, we have two big compilers, GCC and Clang. And you know that the simple way how to switch on or off various optimizations is to passing this -o flags. If you are compiling without this optimization flags, you are basically compiling for debugging, or you can switch off or switch on just the optimizations which are good for debugging with -OG. If you want to play with that, and you will have chance to play with many optimizations during today's homework, there are specific options to switch on or off different optimization passes. So for example, F3 vectorize. This tells the compiler to look into the function bodies and tries to use SIMD instruction to automatically convert your code to use these vectorized instructions and to have it faster. Or you remember from last week, you can also tell the compiler to use this structure packing and so on. This is like the first example that I showed you here with the dates. The compiler can do this automatically for certain data structures to pack those data structures to smaller sizes and so on. So those are many things that the compiler can do, and the compiler can also optimize the code based on the target hardware you will be running it on. So compilers know the properties of the CPUs, of the microarchitectures of the CPU and so on, and can optimize the code for the particular microarchitecture. Yeah, so before we start, I will try to do this. Yeah. Before we start talking about the compiler and about the compiler optimization, let's look at this example. This is a very simple program, which there are 3 vectors, A, B, and C. Each vector is, I don't know, 100 million elements or something like that. And the point of this program is to add, call this function, and to add this vector C to the values of A and B. So very, very stupid operation. We just need to do this addition 100 million times. And in this program, we use the clock function to measure the time. How long does it take to execute this single function, and then we just print it. So just to give you an idea how the compiler can optimize the code. If you calculate, or if you compile this program without any optimization, then on some computer it runs like 0.337 seconds. If you tell the compiler to perform the optimizations, it runs 3 times faster. So you can see that really the compilers can optimize the code a lot. So for production, always use optimization level at least like 0.2, because it is worth the effort. On the other hand, the compilers are not perfect. In many cases, or what the compilers do, basically they have some heuristics. The compilers have heuristics inside, and those heuristics just decide whether to apply this optimization and that optimization. And because these are just heuristics, they can be off. They are simply not correct. Sometimes they try to optimize something which is not important. Sometimes they fail to optimize something which is really important. So what I would suggest to you, and this will be also part of today's example, today's homework. Look at the generated code. If you compile this code with optimizations for some specific CPU. This was the CPU which I had in the past. Nowadays you would use something more modern, and you run object dump -d or some disassemble command, whatever you want. You will see that these are the instruction of the vector add functions. You can see this is the inner loop here. There is some addition add, so this is addition of this A and B, and the result is add to the C, and so on. If you look carefully, you would see that here there is a single instruction, and this instruction is here 2 times. And it's exactly the same instruction. So the question is why the compiler put this instruction here 2 times. And that's actually a question for you. Does anybody know why the same instruction, basically what this is? Take the address stored in RDX plus RAX multiplied by 4. And if you see RAX, we increment by 1 here. So RAX, this is the register which stores this I variable most likely. So here we are indexing this C array, and we are basically reading this element from the array and storing it to register R8D. So there is the first read of this element and the second read of the element. The question is why we need to read it twice. Any idea? So maybe the compiler didn't optimize our code well, right? Maybe the compiler thinks, oh, it might be a good idea to read this I twice. Actually not. The compiler is actually correct here, because if you look at how the arrays are specified, those are specified via the pointer. If one is calling this function, you can call this function not like here, vector A, B, and C, but you can also call this function, for example, vector at AAA. So you put all 3 pointers pointing to the same array. So in this case, it is like A equals A plus 1, and then A equals again A. So you are basically 2 times adding the same, basically multiplying the A by 3. Yeah? And for this reason, the compiler has to put this instruction here, because if you call this function as vector addition AAA without this extra instruction, it would not work. But in our case, we just want to pass 3 different vectors. So the question is whether there is a way to tell the compiler, hey, we are never passing a single vector to all 3 parameters. And yes, there is a way. If you study a C standard, you will learn that there is something which is called restrict qualifier. And if you specify it, for example, to 1 or multiple parameters, by doing this, you are saying, I promise that pointer A will never point to the same memory pointed to B and C. And if you promise this by the compiler, then the compiler will remove this second instruction, and then if you measure how long does it take to execute this function, it will be 0.10 seconds, which is another 10% faster. And 10%, it's not negligible, it's just 10%. Yeah? So by not trusting the compiler, by looking at the assembly code generated by the compiler, you can figure out that maybe you forget some important information in the source code, and you can optimize the code even faster. How you can do that efficiently? Either you do it this old school way by command line and object dump and whatever, or there are tools. For example, a popular tool is Compiler Explorer, living at godbolt.org. This is an online tool where you put your source code, and on the right hand side you can select which kind of compiler with which options you want to use. It will automatically compile this code, shows you the generated assembly, and then you can see how different compilers, different compiler versions, and different compiler switches deal with your code. Here you can see which line gets translated to which instructions in quite easy and interactive way. So if you want to optimize your code quickly, I suggest you just using that. Many, let's say, professionals do that. I am also doing that. If I have some inner loop, some code which I need to run really quickly, I just put it to the compiler explorer, figure out whether my compiler just does the right word, figure out what are the best compiler switches, and just optimize, for example, just in one function in some specific way. Yeah, so this is like high level view of how can compilers help us with optimizing our code. Now, to understand a bit more, we will briefly look into the internals of the compiler. And so to know how the compiler works, or every compiler basically is composed from several parts. So first is compiler front end, and the compiler front end is a part which is responsible for parsing certain language. So for example, there is C front end, C++ front end, Rust front end, Haskell front end, and I don't know. And then the underlying layers can be the same. So this is in case both GCC and Clang or LLVM compiler, this is the case that front end is different for every language, but all the optimization passes, syntactic check or semantic checks and so on, these are shared between different languages, because in the end it's basically the same. Then after the code is optimized using so-called intermediate representation, that intermediate representation is translated by a backend to the target computer architecture. And finally, there is a linker which links different compilation units to a single executable. So you can view this also graphically. So you have different front ends, then you have those optimizers which are common across languages, and then you have backends for different computer architectures. So backend for x86, for ARM, for, I don't know, NVIDIA GPUs and whatever. Yeah. So let's look at those passes at least briefly. So front end. The goal of the front end is to read the source code of your program. In this case, it's a simple function, and the front end produces so-called abstract syntax tree. Abstract syntax tree is, as the name suggests, is a tree structure which represents the source code. I will try to zoom it a bit. So let's do it like this. Can anybody tell me what is this function doing? So any idea?
Square of x?
Yeah, exactly. So the name says it. So it's a very stupid way of implementing square of an x. So x times x. But this is implemented by performing a lot of additions instead of doing just one multiplication. And it's again obfuscated that you are doing just x minus 1 additions, and then you add the final value you edit you edit here. So this is the function, and as you can see, every element of the language is one element or one node in this tree. So for example, there is a for statement, and this for statement has some declaration. This is variable declaration here, and it declares a variable I here, which is unsigned integer. Then there is a binary operator. This is another another child of for statement. Binary operator is smaller. This is the expression y is smaller than x here, and then every variable here is like an element of in this tree. So this is the goal of or first job of the front end, to generate this abstract syntax tree, and then this abstract syntax tree is converted to intermediate representation. Typically, this is implemented in quite simple way. So every node in this abstract syntax tree is somehow represented by a template, and this template is directly translated to intermediate representation. So if we have another implementation of square function which just does what you would implement, this abstract syntax tree is it's a function. There is one compound statement. This compound statement is composed of the return statement. This return statement returns some expressions, which is composed of binary operator multiplication, and the operands of this binary operator are some implicitly casted things. And in the end, there is the x variable here and here. So this is the abstract syntax tree, and this abstract syntax tree gets translated to intermediate representation. Intermediate representation, you can imagine it as an assembly language, but it's an assembly language not specific to a hardware platform, but it's an assembly language specific to compiler internals. It looks like there are some instructions. You can see there is allocate instruction, store instruction, load instruction, multiplication instruction, and return instruction. But these are like intermediate instructions which then get translated to the real machine instruction later. So how does this abstract syntax tree is converted to intermediate representation? Every node has a template. So for example, the template for the for loop can look like this. For loop in a C looks like this. There is a initializer, condition, modifier, and body, and the template looks like expand whatever is initializer, so generate intermediate representation of the initializer, then insert goto instruction, then generate intermediate representation for the condition, put it into the if, depending on the result, go to this label or that label, and then expand body of the cycle, expand the modifier expression, and then go back to the condition. So this is this way the compiler front-end recursively traverses the abstract syntax tree and generates the intermediate representation. This intermediate representation, as I told you, is not the same as the assembly. You can then, or the compiler then converts the intermediate representation to assembly, and as you can see with Clang, you can nicely play with Clang and see the individual steps. So here you can always see the commands which are used to produce this example, and you can, whenever you have this intermediate representation, then you can use this command to convert this intermediate representation to assembly or to machine instructions for x86 or for ARM, and you can see that single intermediate representation can be converted to a different machine code. So this is a front end, and now compiler internals. So I will go through it very quickly because there could be the whole course about compiler internals. So for example, after this front-end work, there are several analysis passes which somehow figure out what happens inside the source code in the intermediate representation. And these are the analysis passes which were part of some, I don't know, 5-10 years old LLVM. There is quite a lot of them, and each of them would require some slide or something to explain. So I'm not going to do that. If you are interested, there is a lot of documentation about these. The point of those analysis passes is to just give the compiler additional information which is needed for optimization. Then each compiler contains a lot of optimizations. Again, I'm not interested, and you are probably also not interested in understanding every optimization, but what you should understand, which optimizations can be done by the compiler and which can't. So one way to understand it is to ask the compiler which optimization it has. We have already talked about this last week. And the second thing is going back to Bentley rules. And some of those, or many of those Bentley rules are, as I told you, already implemented in the compiler. So those which are not crossed, those are typically implemented by compiler. Those which are crossed, you have to implement yourself. Besides those, besides those Bentley rules, there are many others. The compiler optimizations are so-called high-level optimizations and low-level optimizations. So, for example, register allocation. This directly deals with how the hardware is working, and yeah, many other optimizations. So, just to give you an idea, the list of so-called high-level optimizations present in some few years back old version of LLVM is here. So there are, I don't know, 30-50 different optimizations which are applied on your code. And if you are just interested in how those optimizations can be efficient, you can see in this example, this is our weird square function which is implemented in this stupid way. This is the intermediate representation without any optimization passes, so you can see it's quite long code. And this at the right, this is the implementation after all the optimization passes. And as you can see, the compiler was able to figure out that what the function actually implements is just simple multiplication, and it just replaced this for loop with a single multiplication instructions, and all those optimization paths together result in some clever behavior, as you can see. So the point is that you should be aware which optimizations are done by the compiler. You should not try to obfuscate your code by so that the code is unreadable under the sake of optimization, but you should let the compiler doing the job make your code maintainable, readable, understandable, and you should only optimize the part which you know the compiler can't optimize. Yeah, so now I have some animations. If you are interested how this code is optimized, so if you have this code, the compiler starts with this intermediate representation, and then I will just go slide by slide, seeing how the code is changed after one optimization pass. So this is just the animation. You can see the code is shorter and shorter, and at the end it just ends up in with this short version. So these were like high-level optimizations. Those high-level optimizations include things like function inlining, loop optimizations, and these things. And then you have low-level optimizations. There is also pretty many of them, and those low-level optimizations, they optimize the code with respect to the specific hardware architecture. So this is a part. This is tailored to the backend, and there are things like instruction selection. So for each instruction in the intermediate representation, the best instruction provided by the hardware is selected, and so on, and so on. And then there are some, I don't know, branch probability block placement. So this is the thing which helps with branch predictor. It tries to organize the code in a way that the branch predictor of the hardware predicts the branch or not branch correctly, and so on and so on. I'm not going to explain all of this because this would require a lot of time. Again, some animation how code is optimized and converted to assembly, and so on. So this is the compiler internals in a nutshell. What's maybe more important for you and more useful is so-called profile-guided optimization. So, as I told you, many of the compiler optimizations use some heuristics, and those heuristics can be correct or can be wrong, and often it's really difficult to come up with good heuristics which works everywhere. So what almost all compilers offer is so-called profile-guided optimization. In Java, basically Java does the same. Java does it automatically. It automatically profiles your code and recompiles it under the hood. In C or C++ and other compiled languages which do not have just-in-time recompilation, you have to do this optimization and profiling yourself. So with C++ compiler, the approach to do it is to first compile your application with a special switch fprofile generate. This compiles your application in such a way that, for example, whenever there is a branch, like if-else, there is an instruction which records whether if or else branch was executed, and then you execute your program. For example, you run your test suite or some other testing of your application with data, and then whenever this branch is executed during your testing, information whether a branch was taken or not is stored somewhere, and then you recompile your program again, now with different switch fprofile use, and you specify the data which were generated by those profiling runs where the profile was generated, and the compiler now uses the information from those test runs, figuring out which branch was taken when, how many times it was taken, how many times it was not taken, and tries to optimize the code with this information at hand. And basically all big software that you are using, like being web browsers, operating system, and so on, these are typically compiled with profile-guided optimizations, and with it you can achieve quite significant speeds up of your code, like from 10 to 30% faster. So it's definitely worth using this profile-guided optimization. Another thing that I want to mention, because students are often confused about it, is a volatile keyword in C. Volatile keyword is both in C and in Java, and you will hear about what it is used about in Java and how it is used in Java. and then a lot of students think that in C it's the same. So unfortunately not. So it's the same keyword, but it means completely different thing. So in C, if you have some variable which is volatile, for example like this, in C it means, it tells the compiler, do not run any optimization on top of this variable. If I read this variable in my code, just emit the read instruction. If I write to this variable, just emit the write instruction. Don't do any optimization, don't try to optimize it in any way. In Java, this is something different. In Java, it means that the compiler generates barrier and uses a non-cached access to the variable. So this is something very completely different. And have this in mind, don't confuse that. So we are running out of time, so just very quickly. So we were talking about the compiler, and the last step of compiling program is to linking it and producing the final variable. How to do that? This is how you compile your program, and this is how you link your program. So this is like a way which is typically done for you by the high-level compiling tool like Meson or CMake. You don't care about that. But what you should know, that even during this linking, you can somehow optimize things, and even linker can do things which are bad from performance point of view. So you should be aware of them, and you should know how to resolve them. So basically, what the linker does, linker combines several object files together and produces a single executable with all the code in them, and replaces addresses of jumps, variables, memory references, and so on from a so-called table. And basically, what the linker does, linker somehow decides which function and which variable will reside at which address in memory. And as you know, memory is the slowest part of your computer, and if the linker decides the ordering of your functions and variables somehow inconveniently, the result can be slow. So one possible optimizations related to linking is that if you have a set of functions which are called, for example, from a tight loop very often, you want those functions to be stored together. We will talk about that when talking about some cache optimization. If those functions are stored far from away, cache may behave incorrectly. So one way to tell linker, please store this function and that function close to each other, is to specifying an attribute to the function. This is the syntax of C, you can use it. And this tells the linker this is a hot function, and the linker is then instructed to put all the hot functions next to each other, which has some benefits with respect to caching and cache access to the code. Another useful optimization which can be done by the linker is to removing unused code, because at compile time the compiler doesn't know whether a given function is called from another compilation unit. Only linker knows which function is called from another compilation unit, and with some compiler switches you can tell linker, please remove the functions which are actually not used. By doing that, the memory footprint of the program is smaller, and if the memory footprint is smaller, the program is faster. So this is second optimization. And the last optimization, which is quite complex, it is today's compilers are implementing it, but like 5-10 years ago it was not working very well, but nowadays it's finally working quite well. It's so-called link time optimization. And link time optimization means that instead of linking object files together and doing nothing with the code, during this linking process, the linker runs the optimization of the code again, and it can do some like inter-compilation unit optimizations. Typically, it requires quite a lot of memory. Typically, it's quite slow, but can significantly speed up the resulting program because the linker has the whole picture about the whole program, all the units and so on, and can perform some optimizations which are not possible before that. So that's it. I have few things about how the program is executed and how you can speed up the execution of your program, but we can switch that. You can read at that later, and we will talk about profiling at the exercise. Thank you for your attention, and see you later. Určitě.